This presentation was created by Carl Newberg. Carl is a senior applications engineer with Simco Ion. He has been involved in the electrostatics and contamination control field for over 25 years. He's worked for companies such as IBM, Seagate Technology, Western Digital, and Magnacomp Precision Technology, developing programs for both contamination and static control. Carl has been a member of the ESD Association for a number of years, participating in the Standards Organization, the Board of Directors, and various committees within the organization. He co-authored this textbook on contamination and static control with colleagues from IBM. Static charge can cause a number of problems, including contamination and ESD electrostatic discharge. Static is the primary cause of ESD damage to components, contamination of wafers, reticles, and other surfaces where it is critical to maintain cleanliness. Static charge can also cause process interruptions. This happens when an ESD event occurs and the resulting electric impulse interacts with the logic of the processing equipment, causing equipment lockup or other logic issues. All of these ultimately result in yield, reliability, or throughput loss. If we can solve the static charge problem, we can also eliminate many of these other issues that affect product quality. In order to discuss static control, we must start with materials, specifically how those materials react to static charge. Materials can be classified as insulators, such as glass, plastic, rubber, and similar materials. Insulators hold a static charge, and islands of charge can exist. In fact, an insulative material may have islands of both positive and negative charge on them. The properties of the material bind the electric charge and do not allow it to move. For this reason, these materials cannot be grounded. Conductors, on the other hand, have charge that is mobile and as a result can be distributed over the object. Conductive materials such as metals, carbon-filled plastics, and people. People are conductive as well, which is why a wrist strap is so important to keep personnel grounded when handling ESD-sensitive product. When these objects are grounded, the charge bleeds off. There is another classification of materials that falls in between these two materials with respect to their resistance or resistivity. These materials are labeled as static dissipative. These static dissipative materials have some current flow and can be grounded. This allows the charge to flow off the material in a slow, controlled manner. Static dissipative materials are critical when it comes to developing a good ESD control program, and understanding how they work and how they can be developed is very important. It is important to understand that whenever two materials make contact and then separate, static charge is generated on both surfaces. Static charge is generated in a number of ways. Movement of one material across another, rubbing motions. The phase of the material is irrelevant. They can be solids, liquids, or gases flowing across one another. Examples of these may be deionized water being sprayed onto a surface or a vacuum hose pulling particle-laden air through it. Separation of materials is another major source of static charge, such as peeling one material, peeling of a tape or a label off of another. All of these previous charging mechanisms are called triboelectric charge generation. Another mechanism is induction. A highly charged material generates an electric field that can induce electrostatic charge in another object in close proximity to it. Conduction is another method of charging. If one conductive item is charged and it makes contact with another conductive item, they can share the charge. We can also charge a material by ion bombardment. We're going to talk a lot later about how we actually neutralize electrostatic charge by ion bombardment, but if you put too much of one polarity of an ion on a surface, you will actually charge that material up. We mentioned earlier that charge can be induced in a conductive material when in the presence of an electric field. In this slide, this large yellow balloon represents a conductive item, and the flat item on the left represents a charged insulator with a corresponding electric field. As the conductive item moves closer to this field, the charge in the conductive item is polarized and becomes imbalanced. Negative charge is pulled towards the positive electric field, and the positive charge is pushed to the other side, causing polarization of charge in the conductive item. This becomes more pronounced the closer the item is brought to the charge source. If the item is removed from the electric field, the imbalance disappears. In the presence of the electric field, though, The negative charge is bound by the positive field from the insulator. So when the conductive item is grounded, the non-trapped charge is discharged, resulting in a charged item. When the item moves out of the electric field, it has a potential and can be discharged again if touched. Static induction is a complex topic that is quite difficult to understand initially, but it is critical to understand this and avoid it for a good static control program. As we mentioned before, peeling one material from another creates a charge on both surfaces. When two materials join and separate, opposite charge is generated on each surface, as can be illustrated by this example of tape being pulled off of a reel. This slide shows what is known as the triboelectric series. This is a qualitative view of materials and how they interact with each other. Items at the top of the list tend to charge positive, and things near the bottom tend to charge more negatively. Also, items further apart tend to create a greater charge overall. This list is qualitative only, and only an estimate of how materials interact. The diagram on the right side of the slide further demonstrates charging a conductor on the left versus an insulator on the right. The conductor is charged triboelectrically, but the charge is distributed over the entire material and can be bled off to ground. The insulator, however, only charges in the area that is touched, and the charge cannot be bled when the item is grounded. This slide shows Bob walking across the carpeted floor, charging with each step. Then, when he touches the doorknob, the charge on him is shared with the doorknob and in sometimes painful interaction, an electrostatic discharge, also known as ESD. There are always two steps leading to an electrostatic discharge. First, you must charge a conductive item, such as an integrated circuit. The conductive item, in this case, is triboelectrically charged by an insulator. Then the item makes contact with another item that is at a different potential. This concept of different potential is a key concept to understand when developing an ESD control program. If we can avoid having a difference in potential between items through reduction of charge or grounding and keeping everything at the same potential, we can avoid ESD events and ESD damage. The human body cannot feel discharges less than about 3,000 volts. If the spark hurts, it's probably well over 10,000 volts. However, many of the components we are handling in our production areas will be damaged at voltages well below 100 volts. So this means that we can be damaging or destroying components without even being able to feel the ESD events occurring. The other serious problem with ESD damage is that only a small fraction of the damage results in catastrophic failures. Many times, the damage is only partial, and the part then fails later, possibly after it has been shipped and used by the customer. Let's move into contamination concerns. This slide summarizes a paper published back in 1988. The study found that when a wafer had charge on it, it collected significantly more contamination on it than one that had no charge. The greater the voltage or charge on the wafer, the more contamination was collected. The other side of the equation is that the particles needed to be charged. A material that has a charge on it will repel particles that have the same polarity of charge and attract particles of the opposite charge. So how do airborne particles charge? Here are two neutral particles floating around in the air. But then they run into each other, and like all materials that make contact and separate, they charge each other to opposite polarity. Now they are out looking for a surface with the opposite charge to attach to. Not only does the particle get attracted to a surface, but it is bound to the surface and is very hard to remove. It's not hard to understand that if we neutralize the charge on particles and surfaces in a clean room, then electrostatic attraction will not occur. This is another study that was done where a wafer was held at 0 volts for 6 weeks in a very clean environment, ISO 3. Then another wafer was held in the same environment at 2,000 volts. In this case, the wafer that was charged attracted over 23,000 particles more than the uncharged wafer. So how do we solve the problems that result from static electricity? The good news is that in many cases we can solve the electrostatic discharge problem and the electrostatic attraction problem using the same or similar techniques. Solutions can be boiled down to 4 techniques: prevention, dissipation, neutralization, and shielding. We're going to focus today on dissipation and neutralization. Prevention can be accomplished by removing charged items from the work area, the use of antistats, etc. Shielding is tied to packaging in most cases. Here is a room that we're going to turn into an ESD protected area. We will go through the necessary items to make this basic room into an EPA. We'll start with a conductive or dissipative floor and place a workbench, and cover that workbench with a table mat. We will then supply power to the workbench. We may have a floor mat either in addition to the floor or instead of the floor. We also may have ionization. We will have a common point ground. There will be more about common point grounds in a minute, but in summary, it supplies a common point for all these items to be grounded, as can be seen here. We may have a storage rack or carts with equipment on it. The cart would have conductive wheels or in some cases a drag chain. We may have an ESD chair, ESD packaging for ESD sensitive product. We may have a plastic or styrofoam cup on the workbench. Oops, those aren't supposed to be in an ESD safe work area. Then of course, people working in the area, and they are grounded with ESD shoes and a wrist strap. This is a pretty good summary of what a basic ESD protected area should look like. In addition to the cup that shouldn't be there, can you see what else should not be in the EPA? It's the cardboard box. To accomplish dissipation of static charge on a workstation, we're going to ensure that all conductive items are connected electrically, including equipment, people, although we'll talk more about that in a minute, product, packaging, and work surfaces. As was mentioned earlier, this will help control ESD by keeping everything at the same potential. This slide further demonstrates this and highlights the common point ground. This schematic shows the common point ground being a terminal block or similar item. Some people use the metal frame of the table as the common point ground, but whatever you use, it needs to be defined in the ESD control plan. This is tied to AC ground, then wires are used to connect the table mat, equipment, and operator grounding point. In this way, we are keeping everything at or on this workbench at the same electrical potential. We mentioned earlier that people are conductive, so we are going to make sure that all the people in the work area are grounded as well. The wrist strap is the most important and recognized control measure. However, many times wrist straps are ineffective because they are not worn properly or are defective. For this reason, training and frequent testing or continuous monitoring of wrist straps is important. Neutralization. If you have an insulative surface that is charged, it cannot be discharged by grounding. In this case, it has both positive and negative charges on it. Remember that charged areas can exist as islands. If we place this item into an ionized environment with both positive and negative air ions, those ions are attracted to charge of opposite polarity and the charge is neutralized. There are many different types of ionizers available in the industry. On the left are overhead blowers that can be hung over workbenches. These work well to cover entire workbenches. The photograph on the right shows an actual installation where the ionizers are hung from the ceiling above the workbenches. Here, the overhead blowers cover the bench, and on the right, a benchtop blower is used to ionize a smaller area. Here is yet another example of how overhead blowers can be used. When the entire clean room needs to have ionization, ceiling ionization is one possible solution. In this case, ionizers are mounted to the ceiling and the clean room airflow is used to push the ions down to the work surfaces. As can be seen here, clouds of positive and negative ions come down to discharge both airborne particles and materials in the work area. The photograph on the right shows an actual installation of ceiling ionization. Here is another example of sealing ionization. This slide shows yet another example. We can also install ionization in the form of an ionizing bar that can be hung over equipment or a flow hood. We can also use sealing emitters and focus the ionization in areas of high equipment density, etc. Blowers can be strategically placed in equipment to focus ionization in locations where charging is known to be happening or critical assembly steps may be occurring. Simco Ion manufactures several types of compressed gas ionizers that can be used to ionize either air or even pure nitrogen. These ionizers are excellent as they have very tight balance control, fast discharge times, and clean installations. Manifolds can be built to direct the ionization right where it's needed, although the manifold design needs to be carefully designed to provide good coverage. Here are a couple of examples of compressed air ionization installed in equipment. The ionizer on the left is a compressed air ionizer, and the one on the right is a bar-type system with air fed through the ionizer to speed ion delivery to the area of need. Let's move now to another novel use of ionization: reduction of contamination caused by personnel. These two graphs represent studies performed by two different investigators in two very different types of clean rooms. The graph on the left was published by the IEST, the organization that publishes the cleanroom ISO standards. This study was done on a typical electrical fab cleanroom. The graph on the right was done in a pharmaceutical cleanroom and published in the year 2016. These studies show that in a typical cleanroom, somewhere between 35% and 65% of the airborne particulate have humans as their source. So if we can find a way to reduce the amount of particulate brought into the facility on people, we can have a significant impact on the overall contamination levels. We have found that if we ionize the gowning room, we can remove over 1 million particles per person before they enter the clean room. Clothing, materials, garments, all can have a static charge on them, which then attracts charged particles. By ionizing the garments and personnel during the garmenting process, we can drastically reduce the contamination levels. Here are examples of how we install ionization in the gowning rooms. The sealing emitters are installed over the gowning storage and gowning areas. We also install overhead blowers to provide ionized airflow to further knock particulate off of personnel. So, you can see that there are a number of ways to use ionization as a critical part of any static control program. You can't ignore the other pieces either. Grounding must be done properly, equipment must be grounded, and the people must also be grounded. But certainly, ionization is a critical part of the program because there are many insulative materials in the process, including garments, and they all play a critical part.